So, good afternoon, everyone, and welcome to the seminar here today. Our speaker today is Professor Rukmini from ICTS Bangalore. She did her PhD from Stony Brook and a postdoc in Austin. And then after a brief stint at the ISI Kolkata, she joined HRI, where she was faculty for many years, and then she moved to ICTS, and she's now a faculty there. And she will be speaking on Bayesian quantization on even-dimensional compact manifolds, and what? And pullback coherence.
Thank you very much. Very nice to speak here. So, thanks, Amitabha. It will be nice if you stop me and ask questions. I will make it very accessible. And my title is Bayesian type quantization. I'll explain everything. Bayesian type quantization on compact even dimensional manifolds. And pullback coherence. So, the motivation behind this is, so there are many systems. So, usually what people do is they quantize classical systems, right? Using canonical quantization, there are various ways. But our viewpoint is not that. Our viewpoint is any manifold, we want to think of it as a semi-classical limit of a quantum system. What do I mean by that? Supposing you have a manifold, this is a little informal term. So I would say that, yeah, so if you have a function, C infinity function from M to C or R, okay, and supposing you have another one, then F times G is obviously commutating. Right? It's commuting. So now, supposing you are able to give a star product on it, okay, F star, let me just put a H cross in it, which makes it non-commutative. So that this.
In what sense is it commutative?
I mean, just multiplication of two complex numbers, right? So supposing I have F mu into G mu is the same as G mu into F mu.
Okay.
But
it's not
here,
a composition.
It's not composition, it's just multiplication. Whereas I would like to define a star product, which is a different sort of multiplication, which is non-commutative. With the property that when H cross goes to zero limit, F star H cross G just becomes F times G, just ordinary product, and also limit if the manifold has Poisson structure, if it is a Poisson manifold, then the star product could be defined such that G F star G minus G star F times 1 over H cross is I times the Poisson bracket, if there is a Poisson bracket, of F and G. Okay, so this is what we would like to have. So in the H cross goes to semi-classical limit, it is just ordinary classical, it's ordinary manifold. But this, with this star product, you might have seen this super manifold, non-commutative geometry, this terminology, super manifold. Okay. So, but there will be an H cross parameter, and we will see how that goes. Okay. So now, for us, F and G won't be just ordinary functions. There will be a Hilbert space, and there will be an operator acting on it, bounded linear operator acting on it, and then there will be some coherent states, and we will take the expectation value of the operator in the coherent states, which we will call the symbol. I'll go through all this. I'm just telling a story. So there will be a symbol, and on that space of symbols, I define the star product. That is very simple. Quantization. So F will be symbol of an operator, G will be symbol of another operator. I'll define the star product on them such that they satisfy these rules. Okay. That is, in a nutshell, what Bayesian quantization is all about. But let's do it on CPN. That will make it clear. And so now I want to do it also for manifolds which do not have Poisson structure. Right? I want to think of it as a semi-classical limit of some super manifold which doesn't, and this manifold didn't have a Poisson structure to begin with. So how do I do it? My idea is to embed it into CPN, okay, and pull back the structure, pull back the quantization from there, and the point locally, I can pull back the quantization and the Poisson structure from there, from CPN. So that is the idea. So we have to know CPN very well. So this is joint work with Kohinoor Ghosh. We have two papers on the one on in Sigma, and the other one is still in Caltech. So joint work with Kohinoor Ghosh, who was my graduate student. So first let us see CPN. So in Bayesian's quantization, he does CPN in a different way. I don't know how many of you know CPN. Let me just say what is CPN. CPN is a very beautiful manifold, which is almost like CN. So this, I just do this n plus 1 times, crossing Cn plus 1 times, minus the 0. That means this is just 0, 0, 0 n plus 1 times. And then I have an equivalence relation, which is lambda 0, lambda n. So these are n plus 1 variables, is identified with lambda times lambda 0 till lambda n, where lambda belongs to C star. C star means it's a non-zero complex. So what I mean is, there is a product of Cn plus 1, and I remove the 0 element, and I quotient out with this relation. What is the relation? If lambda 0 and so lambda 0 till lambda n is identified with lambda into lambda 0. So all these elements consist of just one point in CPN. So we will call that an equivalence class. So we will denote it like this. Okay. So this belongs to CPN. And because there was n plus 1 variables, right? But since there was an equivalence class, it was there was an equivalence relation. So actually the dimension drops by 1. Okay. So so this is in CPN, and very nicely CPN actually consists of a union of few 0 to n UI. What is UI? UI are all those lambda 0 till lambda n, such that lambda I is not equal to 0. If you recall, lambda 0, lambda n are not all simultaneously 0. So at any point in CPN, one of them has to be non-zero. So I make open charts. These are actually open charts. I'll see how to make it a chart, but you see lambda 0 to lambda n, lambda I not equal to 0. This is a subset of CPN. You agree, right? The equivalence class. This is a subset of CPN, and one can show this is an open set. Okay, because I'm just this is a closed condition which I'm removing. Lambda I equals to 0. Okay, so this is an open set, and these are going to consist of. So what I'm going to try to do is I'm going to divide out, because it's a because it's an equivalence class. I can divide out lambda I not equals to 0, so it depends. It belongs to C star. So I can just divide out by lambda I. Take the equivalence, and let's denote So this is, and this I can denote it by mu 0, mu n. Sorry, 1. So one of them is going to be 1, right? So lambda, so mu 0 and so on. The mu ith one is going to be 1 because it's going to be lambda I by lambda I. Okay, and then this. Given as this. So you see, there are actually nothing but, so you can drop this 1. So it is actually, one can show it's biholomorphic to Cn. So there are all these variables. So 1 is skipped. So 1 is skipped. They write it like this. And mu n. So 1 mu n, the equivalence class. This I can write it as mu 0, mu I is skipped. Sorry, I shouldn't go out of this. Mu 0, mu I is skipped, mu n. Okay. So these are the open charts which makes it a manifold, complex manifold. Okay. So locally, any point must belong to one of these, and this forms a chart. So now we will be working with u0. That means I have divided lambda 0 is not equal to 0. Suppose lambda 0 is not equal to 0. So that is all those, I'm going to write it as like 1 mu 1 till mu n, right? And this I'm going to identify with biholomorphism with mu 1 till mu n. So this is biholomorphic to Cn. This is the chart I'm going to deal with. And the rest of CPN. So this chart covers almost, it just leaves out a measure 0 set. This is almost all of CPN, except there's a measure 0 set left out. Okay. The measure 0 set is given by mu 0 equals to 0. Okay. So we are going to deal with this, we are going to work with this. Now, how do you quantize CPN? So Berezin quantization of CPN. So in Berezin's paper, this actually, since there is an SUN plus 1 acting on Cn plus 1, that action actually descends to CPN. So it is actually a homogeneous manifold. Okay, homogeneous means there is a group action which takes any point to any point. Okay, and it's a quotient. So I won't go into the whole story, but Berezin uses that fact to quantize CPN. But we want to give it a local description because we want to pull back to general manifolds, right?
Why do you say SUN and not UN?
SUN plus 1.
Why not UN plus 1?
You could write it as UN plus 1.
It's just N plus 1 complex variable, right? So,
yeah, but I think if you want to, actually there is a coadjoint orbit description.
Okay.
CPN can be thought of as a coadjoint orbit, and that, as far as I know, is just SUN plus 1 mod out by S UN cross S1. UN.
that UN goes away.
Yeah, so these are the ones which, so there's a coadjoint action on the dual of the Lie algebra, and this is the one which fixes it. So the orbit is this. So this is CPN. So CPN has many descriptions. This is one of them. Okay. So now, whatever it is, Berezin uses this fact, this kind of homogeneity. Okay. But what we want to do is just see the whole thing using coordinates. So very importantly, there is a scalar structure on CPN. So how does that look like? Scalar structure on CPN looks like, so we are going to restrict it to U0. Okay. And so it's given by, so U0 remember was given by mu1 till mu n. Mu0 at 1 became 1. So this is the running variable. And this is called the Fubini-Study metric. And how is it done? How is it written? It is something like this. d mu I with d mu j bar, where this is a this omega ijfs is a invertible matrix, and it has very nice property. It is actually a Keller. This whole thing gives you a Keller form. I won't go into what a Keller form is, but for our purposes, it can be gotten from a what is known as a potential. Okay, and the potential is given by, you just make this function phi fs mu bar is ln of 1 plus summation I goes from 1 to n mod mu I square. Okay, and you write the metric, Keller metric as del squared phi, this fs del mu I del mu j bar. Just take double derivative of this. Okay, that is my Keller metric coefficients, and omega I j fs is nothing but I by 2. What did I write? Yeah, omega I j fs g I j fs. This is what it is. And what is the Poisson structure? Given a Keller form, you can always, or even a symplectic form. Symplectic Keller form is a symplectic form which has some nice properties, so, which is compatible with a complex structure. So whatever it is, I won't describe the Keller structure, but you can define. Supposing there are two functions, P and S belongs to C infinity Cpn, it means C infinity function with Cpn, then you can define their Poisson bracket to be summation. This is a general standard thing. If you have a symplectic form given by this omega ijfs, it's invertible. So then actually you can write the inverse matrix. Okay, del T, the usual thing, del T mu j bar, del S, del mu I minus del S, del mu. I may be making a mistake, so I think it's just S and T S and T interchange, right? So del T, del mu I. This is how it looks like. Okay, and this is an invertible matrix because Keller form is symplectic and symplectic is non-degenerate. So this matrix actually has an inverse, and this is the inverse matrix. You can construct always from a symplectic form, you can construct the Poisson bracket like this. Okay. And now I won't go into all the details, but now how do you find the Hilbert space of quantization? What is the suitable Hilbert space of quantization, and what are the coherent states? So there is a line bundle called the hyperplane line bundle. So CPN has a line bundle called the hyperplane H. So this is called the hyperplane. I think hyperplane section line bundle. We have just called it hyperplane bundle. Okay. And the nice thing about this is its curvature. Curvature of this line bundle is actually just I by 2 pi or something times the Keller form. Okay. So this is proportional to Keller form. Okay. So this is the candidate for the Hilbert space because of various reasons is sections of this. But this is actually too little. I mean, the sections are not too many. I'll just say in a minute. You want a large number of sections, right? You want the Hilbert space to be finite dimensional, but have enough sections. So what you do is you introduce this parameter m, which is 1 over h cross. Okay, m is 1 over h cross. So basically, therefore when h cross tends to 0, limit will correspond to m.
Can I just go back to this? what is the difference between an ordinary line bundle and the hyperplane line bundle?
Hyperplane line bundle is a line bundle. It's called hyperplane line bundle.
Right.
It's actually the dual to the universal bundle, and its sections correspond to can be associated with hyperplanes in CPM.
Well, line bundle is something whose sections are basically functions.
I'll come to that. How sections are like locally they are functions. On
Right.
U0 they'll be
Right.
functions,
Right.
and I'll just come in a second. I am coming to
Okay.
that point. Okay. So what I do is H tensor M is my line bundle. I just tensor it M times, and what are its local sections on U0? On U0 the sections look like polynomials in degree n variables, polynomials of degree less than or equal to n. So let me just say in a minute what that means. So supposing you have mu1 to the p1, mun to the pn. This is a polynomial in n variables, and the degree is sum over p1 plus sum of p1 plus pn equals to p. Okay, and you just let all such polynomials whose degree is less than or equal to n. All such polynomials. So these are multinomials, and this. Okay. So
this is how you are defining the.
no, this is actually sections of H tensor M. This can be proved independently.
Yes.
But these turn out to be my Hilbert space. Just assume it for a second. This comes from geometric quantization and many other considerations.
And
Okay.
this value P comes from what? This is any
P is any P less than M. I am fixing my M.
But M is so you define.
Later on, I am going to take M to infinity. But
M you have already taken to be an integer.
Integer. 1 over H cross is such that it's going like an integer, suppose. Okay. So 0 less than P less than N. Okay. And you can normalize it. So there's an inner product. Let me write the inner product because that is very, very important. So my Hilbert space is going to therefore consist of span of polynomials like this. Mu1 to the P1, mu1 to the P1, mun to the Pn. P is less than or equal to M. So P1 plus Pn equals to P, and all such possibilities. Okay, that is my Hilbert space. And then what I do on, so now I want to get a orthonormal basis with respect to a Hilbert's inner product. And what is the inner product? The inner product you can define like this. F times G. Again, everything is going to depend on it. That means H cross. Okay. So there's no chalk. Okay. So this thing is Cn integral of F mu bar G mu V V mu divided by 1 plus mod mu squared to the power n, where dV mu is the volume form on CPN, d mu with d mu bar divided by 1 plus mod mu squared to the power n plus 1. This is the volume element on CPN. And I have this factor which depends on it. Okay, this is important. And with the respect, and Cm is just the with f and g equals to 1. Cm is 1 over integral of 1 over 1 plus mod mu squared to the power m dv. It's a normalizing thing. Okay. So now, with respect to this inner product, we can actually.
So mu is the coordinate on U0.
U0, exactly. So in the integral is on U0. It just gives you a set of measures 0. So this integral can be extended to all of CPN. Okay, but then you have to be careful because on that other set of measures 0, actually you cannot use these coordinates mu1 till mu1. And then you have to be careful. So that is the only problem. So we will just work with Q0 for the time being. Okay, and with respect to this, H can be normalized to be, let me call it span of phi I, where phi I, this multi-index, it's that polynomial only. Where is it? Anyway, whatever it is, it's the polynomial. But then I divide out by some, the norm of it. Let me write it as P1 till Pn semicolon P. That means sum of Pn is equal to P. Okay, so this is my D. How do I write it? With a bracket. Okay, and I is the multi-index P1 till Pn P. This is the multi-index, which means I have these integers which sum up to P.
What is D?
D is just a constant,
Not
which
the measure.
normalizes it.
Is it the measure?
Not the measure. I want an orthonormal basis. So one can show that these are actually orthonormal. So I have orthonormalized it. That's all. So it's basically I plug in phi I bar, and phi I, and whatever I get is my D, the normalizer. Or do I do square root? Let me just check. I think I need to do square root.
Why is it 0?
Huh? Yeah, so that is very simple because when you have in U0 is more or less like Cn, right? So if, supposing you have in um, in C, even in C, mu1 bar, say mu1 bar to be P1 and mu1, uh, say mu1 to be P2. Something like this. The only time, and you are integrating it on all of C. Let's just do it for one variable case. And then this will be like mod mu1 to the P1 plus P2. But then there will be a e to the I. What will it be? P1 minus P2 into theta. Right? And when you integrate this, this is going to contribute, the theta integral is going to go if P1 is going to give you 0 if P1 is not equal to P. So that is the reason this polynomials become orthogonal.
Because it is binomial to C.
Yeah, like each individually, actually you can do it. I mean, this is just a reasoning I'm doing. You have to show it, but this is the reason why it's happening. So see, there'll be a mod. Supposing on C you are doing it. So mod mu1 is suppose R, and theta e to the so there's a d theta integral. The d theta integral will vanish if P1 is not equal to P, because you're going right wrong. Right. So that is the same reason why these become orthogonal. Okay. Now, how do I construct the coherent state? This is a. I'll tell you why I'm.
When you actually do that integral, you will also have the measure, right?
Yeah, yeah. There'll be a measure in the bottom, but that only depends on mod mu1. So what I'm saying is there'll be a 1 plus mod mu1 squared to the power n or something like that, right? N plus 1 actually. So here it's n plus 2. So whatever it is, it's a function of r only. So the theta integral actually contributes to 0. P1 is not equal to 0. Right? So now, given a Hilbert space, there are these things called Ronsley coherent states, which can be defined like psi mu is summation phi I is that multi-indexation polynomial, which I often normalize, mu bar phi I. So basically, an index mu belongs to CPN or Q0, let me call it. Okay, and I evaluated at phi I at that bar and phi I. So this is a coherent state, and you may ask, Why are you calling it a coherent state? So there are various reasons for it. One of them is it satisfies very nice properties called reproducing kernel property, resolution of identity, and so on. So let me just write all the properties it has. Because of the orthonormality, one can show very easily that it has the reproducing kernel property. In physics, you call it something different. I think in physics, this leads to that maximal likelihood property. You may have heard about that in these classes. So this leads to that, but we call it this. So basically, it has the nice property. This inner product is that inner product. So psi mu psi inner product, the MF inner product, is psi. So any psi you take, that means anything from the Hilbert space, you evaluate it at mu, that is given by this inner product. Okay, that's number one. This can be easily shown. Then number two is the resolution of identity. This you may have seen in resolution of identity. Resolution of identity is Cm integral Q0 psi psi mu, sorry, switching too much. And then I will have to multiply by the Keller potential. So that and B mu. Okay. And that's nothing but the inner product between psi 1 and psi 2. This you may have seen it with bracket notation.
But for this you need a completeness, right? So without completeness,
Yeah, it's a complete inner product. A complete Hilbert space. Yeah. So basically,
and the basis has to be complete, right?
Yeah, it's an over complete. Yeah, yeah. So I should have probably mentioned it. Actually, it's an over complete basis because phi I themselves were a basis, and these are far more. This is a linear combination of phi i's, but they are far more. Mu every point in CPN is giving you a coherent state, which is a linear combination of the basis. So it's actually over complete. So let me just finish writing this. So. So there is a CM in front. Yeah, very important, this CM. Otherwise, we won't get the right properties.
So these psi mu's are not
psi mu's are not orthogonal.
they are not orthogonal.
They are not
Because
orthogonal.
they form an overcomplete.
They are form an overcomplete basis.
This first property that you wrote down, this also we is the same as we write in bracket.
Yeah.
Something like
exactly.
h psi psi x is psi x.
Yes, exactly.
So why do you call it this reproducing kernel property?
Oh, that is
Maximum
because.
likelihood? How is it related to maximum likelihood?
Yeah, maximal likelihood property, right? It is what do you say? The coherent states are almost very close to a classical state. That's the maximum likelihood. So I will just now I don't remember exactly how we phrase the maximum likelihood property, but and reproducing kernel property is similar. They use it in harmonic analysis. So they call it reproducing kernel for that reason. Okay, now, what else do I want to say? Yeah, it's over. Number 0 is over complete, which actually follows from this also. So now what is there is in context. So now supposing so these are called coherent states. So now supposing I have a bounded linear operator from the Hilbert space to the Hilbert space. So bounded linear operator from this Hilbert space to the Hilbert space. So
the second relation is the completeness relation for psi mu's.
Yeah.
It is a completeness relation.
Yeah, like you integrate it on the mu's. So basically, you may have seen it like this. Integral with some we knew, and for us, instead of so for you, for physicists, this is just the volume form, but we have defined the coherent states in such a way that this thing also comes out. For example, this actually tallies exactly with your usual coherent states for simple harmonic oscillator or spin. Uh, except, I think, except that there is in simple harmonic oscillator, there is this term, if you remember, right? So this term, instead of putting it in the coherent states, we put it here.
Probably that exponential factor can be put in
this entire thing, exactly.
In the form of a star product kind of thing. Maybe can introduce a star product in between those two inner products and absorb that exponential factor. That's the ordinary product. No,
this is
what
just
what I'm saying is that e to the power minus n factor that can be probably put in. I can probably absorb that factor at the cost of putting a star product.
Maybe that's what's happening. But what I was trying to say is, usually you define it with this inside the sign.
You absorb it in the
states. Yeah, usually. I think that's what's happening, but I can't be absolutely sure. Okay. So now, so now you have a bounded linear operator from this Hilbert space to Hilbert space, and what I do is I just take inner product of the, so this is the expectation value of A hat on the coherent states, and I divide by sin u sin u. So this I call it A mu bar, or A mu bar. A mu bar. So A hat acting on psi mu in a product with this thing. So I guess you will call it the scattering amplitude or something, right? When you take is the expectation value. Okay,
it's a matrix element.
It's a matrix element. And the nice thing about this is that since these are coherent states, the diagonal from the diagonal itself. So if you knew A nu bar, then you should be able to get back your A hat. You can reconstruct your this thing just from the diagonals, because the coherent states are that way. Okay, this is very special about the coherent state expectation values. Okay, I can write the formula, but I'll skip that. So you can recover from A mu bar A hat. So it encloses all the information you need. So now on this A hat, I want to define a star product. Why? Because supposing I have A1 hat and A2 hat, I have a composition of these operators, right? Which is non-commutative. And what is its symbol? Its symbol, I'm going to write it as A star. Its symbol. That means its expectation value on coherent states divided by the norm. So this is what I'm going to define. And that is a little bit complicated definition, but it makes very clear sense if you work it out. So let me just write the integral finally. So A1 star, this is the symbol. A2 mu bar is defined by this huge integral on Q0. A1 mu bar, A2 mu bar, L of m mu bar, I'll just write what is L of m. L of m is nothing but psi mu evaluated at mu. Let me just define this first. I just wanted to keep it consistent with Berezin's paper. That's why I introduced all these notations. It can be thought of simpler, but where L M mu bar is nothing but, by definition, it's one of the one coherent state evaluated at the other point. So which one it is? Uh, yeah. So it is L mu bar is nothing but psi mu in a product. It is psi mu evaluated at mu. Okay, it's that coherent state, the mu at coherent state evaluated at mu. That this kind of huge expression, it simplifies a lot, but they want to keep it very general, so they wrote it like this. Berezin also has this expression. Berezin has this expression, and so now I'm not going to write all the details. This star product has this nice property. How much time do I have? 15 minutes. That will be enough. So the nice thing, I'm not going to prove it. It requires a little work, but one can show. So remember, everywhere it depended on H cross, which is 1 over n. So this has the correspondence principle. This is called the correspondence principle. Correspondence principle, that is limit m tends to infinity a1 star a2 mu bar is just in the m tends towards infinity, that is h cross goes to 0 limit. It is nothing but product of the symbols. The star product just becomes ordinary product. And the second fact is, number 2, limit m tends to infinity a1 star a2 minus a2 star a1. This becomes exactly I times a1 a2 Rukmini to the Poisson bracket. Let me write it Poisson bracket. So basically, A1 star A2 minus A2 star A1, the commutator corresponds to the Poisson bracket. This is one criterion for it to be a quantization. Remember, Dirac's condition was one of them. Right? You want operators to be representing your observables, and if it acts on a Hilbert space, and then the commutator of the operator should correspond, when in some classical limit, should correspond to the Poisson bracket. That was Dirac's condition of quantization. So these two correspondence principle must hold, and they do hold for this. Okay, so this is a little work, not too much. So now, what is our idea? Our idea is there are many ways of doing this, but and also another point is for certain. So Berezin did it. He used this definition. For CPN, as I said, he used the homogeneity, but for other manifolds, he used color structure. So for some color structures with some properties, he actually could show Berezin quantization. Not all Kähler manifolds. Some Kähler manifolds, he could show Berezin quantization. That was Berezin's seminal work. Okay. And so the paper is very hard to read, so we thought we'll do all the details ourselves and see what's going on. Okay. So that was for CPN. Now our idea is, I have N. Any arbitrary compact.
Before you go on,
Yeah.
there is also do this for like Gassman.
Gassman, yes.
They define the.
No, I don't think.
His integration was defined for Gassman.
The Fubini study is defined by.
There is also defined the Gassman integration. Right? So the usual thing that we do for them is quantization.
Fermions. Oh, that's what
So
you are
Berezin
asking.
defined that.
Oh, he defined that.
Yes.
The I
In
don't.
terms of
I'm not
Grassmann
aware
variable.
of that.
So I was wondering if he used Grassmann variable.
No, in that paper he didn't use mention Grassmann.
But later some.
The Cipians are of course special cases of
Cipians
Grassmann.
is-
Yeah. But I don't. Grassmannians are also homogeneous spaces actually.
Okay.
So he did it for many homogeneous scalar manifolds. So he might have done it for Grassmann. That's a very good point. I'll just note it down. Yeah. So
So then
maybe
instead of
homogeneity.
commutators, he'll consider anti-commutation.
Uh,
Anti-commutation.
no, there will be both things coming.
Yeah, both.
Yeah.
I mean, the graded manifold.
Yeah, I think so. I'll just
Yes.
so Berezin quantization of Grassmannian manifolds.
They're only graded manifold.
Yeah, I don't know this
Okay.
part, but I think it can be done using this homogeneity
Okay.
construction. So,
Another thing,
yeah,
so
yeah.
far, when you have introduced already the star product and you have introduced the correspondence principle, and it should reduce to the usual things and the Poisson brackets.
Yes.
But what is the form of the star product?
Yeah, that integral I wrote, that long integral.
We have already did it.
Yeah.
L by L.
LM, I mean, just to be consistent with his notation, I use the LMs, but they are just coherent states evaluated at the mu coherent state evaluated at mu, all those things. So that expression is actually very simple for usually, but
So for CPN, it will simplify quite a lot.
quite a lot. It will simplify quite a lot. So I just wrote it like that because it's consistent with his definition. So
So will it reduce to any of the standard known forms like Moyle star product or Burroughs star product?
This I don't know. That is also another good question. Moyle product may be related to this.
Yeah.
No, that was exponentiating, right?
Yeah, yeah.
This
Burroughs is also exponential.
which one?
Burroughs product. Burroughs.
Oh, I have not heard about this. So, Moyle product. That's a very good question. I don't really know whether it's related to the Moyle product. Maybe. It's a form of deformation quantization after all. H cross you can expand in H cross and see. Yeah, so it could be related. So our idea is very simple. I'll just tell the idea, not get this thing. So arbitrary, even, compact manifolds. So one first thing we do is we remove a set of measure 0 such that it becomes, so this is 2D, this becomes CD. Okay, what do I mean by that? So supposing you take the sphere, for example, you remove a point, then it's biholomorphic to C, right? Similarly, if you take a torus, if you remove these two circles, okay, then it's biholomorphic to C. So what I'm biholomorphic or diffeomorphic to C. So this is a set of measures 0, which you can find in general. A manifold, a topological manifold is made out of cells, cell decomposition. So you add bit by bit you construct, right? Zero dimensional cell you attach uh, uh, even dimensional manifold say. Then you attach cells in a certain way. You glue it up in certain way, and finally you attach a 2D dimensional R2D cell. A cell which is this thing to R2D, diffeomorphic to R2D, okay, homeomorphic to R2D. So, for example, this one you had a point and you had this, you attach this to this point to get the S2. Similarly, here you had this and you attached one skeleton to uh, make the torus. So basically, you should be able to find in every manifold, if you remove a set of measure 0, there is a special set of measure 0 of which is of dimension less than the top dimension, such that if you remove it, it's actually just the plane CD. CD, okay. So this is 2D dimensional. This is real, and then this part. So supposing I have this part, I remove this. I'm going to M. So this is CD. I'm going to, in general, this will be M. I'm just writing the torus just as a, yeah. So M minus M0. I'm at a diffeomorphism. Let's call it tau to CD, which I embed in CPD as U0. This is going to be embedded in as U0. Okay, and then I do the entire thing on U0 in CPN, and what's left is a set of measures 0. And I hope that it's going to extend to that set of measures 0. And the entire thing will depend on tau. You may say, oh, that means all manifolds that you're getting from, but it's that pullback. When I pull back the quantization from CPN, the Hilbert space, the inner product, everything is going to depend on the tau. And that's going to change from manifold to manifold. Not every manifold we are doing the same thing. Okay. So this is how one way of doing it. Another way of doing it is, and of course you can take another. You can say, okay, I'm not going to take this. I'm going to take another measure 0 set which I'm going to remove. So then that is homeomorphic to CD with a tau prime, which is sitting inside as U0 in this. So tau prime, now I have to relate this quantization which was pulled back from here to this quantization which was pulled back from here. I meant by quantization is I am pulling back all the Hilbert space by this tau and tau prime, and also the inner product, and also the what do you say? The operators have to the quantum operators have to satisfy some relation. They can't be arbitrary. Okay. So because the Hilberts, so they have to have some relation, uh, uh, and I'm not going into all the details, but that's one way of doing it. And one can show again that, so if A1 hat, supposing I just take this direction, so A1 hat star A2 hat, where I pulled back everything from CPD, again satisfies correspondence principle because they satisfy correspondence principle in CPD. Okay, this is a bit of a calculation, but it can be done.
And these operators Hermitian, so are they by construction Hermitian?
No, not necessarily. They are just bounded linear operators. Hermitian. I don't think any Hermitian. Just bounded linear operators. I pulled back the Hilbert space by tau and constructed those operators again by pullback by tau and so on. Okay. So now another way of doing it is in complex manifold. Supposing you have a manifold which is complex. That is very nice. Again, you may have to. So this is very nice because there is a biholomorphism of each open set to CD. Actually, not CD, not always CD. It's a polydisk. Okay, here the subtlety comes because a polydisk is not biholomorphic to CD. Okay, so in several complex variables, there is a lot of problem. It's, for example, in just single complex variable, you know that the disk is biholomorphic to a polydisk. Okay, but in a disk is biholomorphic to any, like what I mean is, in the complex plane, a disk is biholomorphic to any region like this by Riemann mapping theorem. Okay, but for CPD, that's not the case. So you have the polydisk and you have the disk. They need not be biholomorphic at all. Okay, in CPD. CD, sorry, I mean CD. Biholomorphism doesn't work. So you have to be careful, but this polydisk actually helps a lot, and you can you can embed it in CD and again do the same thing, pull it back from CPN. So locally you will be having a Hilbert space which you have pulled back from CPN, and then you do it by patch. So in the there is a what do you say, biholomorphism going from this patch to this patch in complex manifold, and you should be able to glue up the whole thing using that. So that's the idea. But again, because of this complication, again you have to leave out certain sets of measures. So that's, and oh, one more thing. So you may ask, why did we use CPD and not CD? Just CD directly. But CD has an infinite dimensional Hilbert space, non-compact, whereas CPD has a finite element. So if you are expecting from your problem, whatever is the problem you want to solve, you are expecting an infinite dimensional Hilbert space, then you pull it back from CD. That's why it works. But if you are expecting uh, uh, finite dimensional Hilbert space, it makes more sense to pull it back from CD. So that's one way of doing that. Not saying that's the only way. There are many other ways probably, but this one way we have done. So that means for every manifold we have constructed a super manifold in a sense. Patch by patch we have glued it up such that in the limit it goes to that. In the limit it goes to 0. It goes to that. In terms of operators in Hilbert space, it's not function level, but in terms of operators in Hilbert space, we have constructed a supermanifold whose h cross limit is that even dimensional manifold. So, okay, I understand.
So I had a question already at the beginning of the talk. So this H bar that you have introduced, is it in some way linked with the Planck's constant?
Yes,
Maybe.
yes,
It is
yes.
the Planck's constant.
Yes, it is the Planck's constant. And the Planck's constant is very small compared to the length of the length prevalent in the problem. Then it's the classical limit. It should represent the classical limit. That's why they say H cross goes to 0 limit. So, and also thanks for these two Rachmaninian manifolds and the Moyle product I should really see. Thanks for these two points.
Do you have a Hamiltonian somewhere? Do you need to
Yeah, that's a
check
good
some
point.
things in this?
That's a good point. The AHEP. What if you had the AHEP corresponded to quantization of a Hamiltonian?
I mean, you don't need to have a Hamiltonian system. Right?
Yeah, you don't need to, but your AHEP could be like say p squared plus q squared is available to you, and you do some kind of quantization of p squared plus q squared to get an operator h hat or something, a hat that acts on the Hilbert space. And can you do something like this here? Is it a bounded linear? I'm not sure whether it's a bounded linear operator. We are only talking about bounded linear operators because otherwise things are going to be very crazy. You cannot define the star product, I think, unless in some cases.
Well, if you have a finite dimensional, but you should be able to define a boundary.
No, I'm saying the
If you have a
Hamiltonian.
finite dimensional universe,
Yeah.
then
Then
probably
it will be bounded linear
you should be able to define the Hamiltonian.
in a bounded linear. Yeah. So, but then you are actually seeing what is the Hamiltonian's relation with other operators.
Right.
You star product.
Yeah, see, what I was thinking is that whether you can define like a set of commuting operators.
Set of
Commuting
non-commuting.
commuting operators.
Oh, I see.
When you have a
With the star
Hamiltonian
product.
system,
With the star product.
with whatever, because there is a quantization.
Oh,
Whenever you have a quantization, you have to define some kind of set of commuting operators.
commuting operators.
Hamiltonian and other commuting operators.
Yeah.
that's it.
Yeah. So, like H hat commuting with a set of operators.
Right.
and
Mutually commuting.
mutually commuting, like in an integrable system.
Right. Right. So you can get some integral solution.
Some integrals of motion. And then you look at their symbols,
Right.
do the star product
Right.
and see what it
Right.
actually means in
Right.
terms of this. Okay, that's also nice. No, I've not thought about this area, these directions. So let me just write that also down
Okay.
because I forget sometimes. So
So you can
AHEP,
apply it to Hamiltonian system.
yeah.
What is the star commutator of A1 at an equivalent? The star commutator.
Star commutator. Yeah, so is that long integral?
Okay. It's a big expression.
It's a big
For
expression.
CPN, what would be the answer?
For CPN also it's an integral values. In general, if you have specific things, it will reduce to very nice things. But the star product, what's that integral with a length and all that? A1 mu nu bar, A2 mu bar, and so on. And then you integrate the mu, and those coherent states will appear. Psi mu nu. So that huge expression, and then you do the one with the reverse. A1, A2, and A2, A1 reverse. It won't be the same thing, and then so that is yeah. So I don't really know. This is in the domain of non-commutative geometry, and I really don't know what is going on really, actually deeply. But we just try to understand.
Okay. Let's see outside.
So it was understandable, right, to everyone, more or less.
This biholomorphic thing I don't know.
Yeah,
No.
biholomorphic is
By
this way there is a